All right, today we're diving into the physics of a crash. We're talking about the science of impact itself, from the sharp crack of a pool break all the way to the crunch of a car crash. And it really all boils down to one simple question.
I know, right? It sounds like a strange comparison, but the answer, well, it actually gets at some of the most fundamental rules of our universe. See, both of these are just examples of collisions, and believe it or not, they're governed by the exact same laws of physics. So let's break down how that works.
Okay, first things first. What even is a collision? Well, at its core, it's actually pretty simple. It's just a really brief moment where objects exert these super powerful forces on each other. Think of it like a powerful exchange of force that happens in a split second. That's it. All right, so if we're going to understand any collision, we've got to start with the single most important concept. It's this unbreakable rule of physics. It's called momentum.
This right here, this is the law of conservation of momentum. So what is momentum? Just think of it as an object's quantity of motion. And here's the crucial part. In a collision, you can't create it and you can't destroy it. You can only move it around. The total amount you have before the crash is the exact same total amount you have after.
And a game of pool illustrates this idea perfectly. Okay, picture it. Before the break, where's all the momentum? It's all packed into that one moving cue ball, right? Then, bam, impact. In that split second, the momentum gets transferred. And what happens after? The cue ball slows way down, maybe even stops, and all the other balls scatter across the table. They now have the momentum that the cue ball used to have. See? It wasn't lost, it was just passed along.
Okay, so if momentum is always conserved, that brings up a big question, doesn't it? Why does a clean pool break look so different from a messy car crash? Well, the answer lies in the second part of our story, energy.
And here's the twist. This is where it gets really interesting. Unlike momentum, the energy of motion, which physicists call kinetic energy, isn't always conserved. It can be lost in a collision. And when I say lost, I mean it gets converted into other stuff, like the sound of the crash, the heat from friction, or the energy it takes to physically bend all that metal.
This brings us to two basic types of collisions. First, you've got elastic collisions. Think of our pool balls. The objects bounce off each other almost perfectly, and that kinetic energy is conserved. But then you have inelastic collisions. That's our car crash. The objects deform, they make a ton of noise, and that kinetic energy isn't conserved. It's lost. It's what becomes the crunching sound in the bent metal frames.
So physicists actually have a way to measure this. It's called the coefficient of restitution. Yeah, I know, it's a mouthful. Let's just call it a bounciness score. A score of 1 is the highest you can get. That means a perfectly elastic collision, a perfect bounce with zero kinetic energy lost. And that's pretty much what you see with billiard balls. Now, on the complete opposite end of the scale, you have a bounciness score of 0. This is what happens when objects don't bounce at all. They just stick together after impact. This is where you see the absolute maximum amount of kinetic energy get converted into other forms. And that, of course, brings us right back to our car crash. When two cars collide and end up as one single tangled mess of metal, that is a textbook, perfectly inelastic collision. All that energy of motion didn't just disappear into thin air. It's what did the damage. It's what bent the steel. Okay, so far we've mostly been talking about simple, direct, head-on hits. But life is rarely that simple, right? So what happens when the impact isn't so straightforward? Let's see how these rules hold up when things get a little more complex. So yeah, what if it's not a direct, head-on hit? What happens when things collide at an angle? Does our big, unbreakable rule about momentum still apply? Oh yeah, absolutely. The secret here is that momentum is conserved in two directions at once. Think about our pool table again. You've got the momentum going up and down the length of the table. We can call that the x-axis. And you've got the momentum going across the width of the table, the y-axis. The total momentum has to be conserved for both of them independently. So that unbreakable rule, it just applies twice. And that is the physics behind every single amazing bank shot you've ever seen. Okay, let's pull this all together. We've got this unbreakable rule of momentum, and then we have this variable story with energy. We've got bounces, and we've got crunches. So why does any of this physics actually matter in the real world? Well, believe me, this is not just textbook theory. Engineers use these exact principles to design crumple zones in cars. Those zones are specifically built to have an inelastic collision, to crunch and deform, to absorb all that crash energy so it doesn't get transferred to the people inside.
It's absolutely crucial for sports science, for understanding how giant particle accelerators work, and even for predicting how planets and asteroids interact out in space. Seriously, this stuff is everywhere.
And that kind of leaves us with one last big thought to chew on. If every single collision, from a tiny particle to a giant galaxy, just transfers momentum, if it's all just being passed from one object to another, like a cosmic baton in a relay race that never ever ends, it makes you wonder, doesn't it? Where did all the momentum in the entire universe come from in the first place?